Okay, thanks, Paul, and good evening, everyone. This is my first COVID-era talk, so it's been a while for me talking to a group of people in the flesh. So this is a nice return to some kind of reality. So thanks for asking me to come along. So today I'm going to talk about some work that we've been doing over the past 7 or so years on manganese in Western Australia. And as this work has developed, we've come to realize that there's very much a misconception of the temporal and geochemical depositional ideas that there are globally around how and when gigantic manganese deposits form and when and where they occur. And I'd like to suggest that we in WA have a very, very good opportunity to capitalize on battery metals in general, one of which is manganese. So before I get into the geology of things, I just want to give you guys a quick overview of manganese as a commodity in a battery sense, if you're not familiar. Manganese is generally the other battery metal that no one really is talking about. So we've got I didn't realize this was going to be so dark, but this is something I've nicked from the Visual Capitalist from a couple of years back. We've got cobalt and nickel. These are the really commonly discussed, popular, fashionable battery metals, which are high value. All the explorers are very keen to go and find this. And if you find a decent deposit of these battery metals, and well, that's better. Then that's all good. But manganese is comparatively really low value. It's common. There's a huge supply globally, whereas cobalt and nickel not so much. But when we look at the uses of these different battery metals in terms of popular modern batteries, manganese actually occurs in quite a lot. So in the Tesla Powerwall, for example, it's 33% manganese in the cathode. The Nissan Leaf electronic vehicle is 100% manganese in the lithium ion battery. Whereas others like the Tesla vehicles and iPhones and things use more high value metals such as nickel and cobalt. Now it's too dark, I can't see the thing. Okay. Very quick overview of the different chemicals that go into these. So this is all stripped from Battery University, which is basically the global hub of everything that everyone knows about modern battery research. The three main battery types, or lithium-ion battery types that we think about battery metals at the moment is lithium cobalt oxide, lithium nickel manganese cobalt, or lithium manganese oxide, right? Okay, I'll let you read those. But basically, these two are essentially high cost and high performance materials, whereas the lithium manganese oxide, which is this spinel structure with lithium ions involved, this is a much lower cost product. And as I'll explain in a second, these two are going to just rise in cost as nickel and cobalt resources dwindle. And this just kind of highlights that this is a table of different battery types and some of their energy and power parameters and costs. And what we see really is the manganese batteries are of comparative low cost compared to some of the other ones. Oh, sorry. What I really want to show though is, spelling mistake there. Manganese for steel making is a really cheap commodity, so it's typically less than $10 a ton for a medium grade manganese stock feed. Whereas some of the battery materials that we need for manganese batteries, such as the electrolytic manganese dioxide, manganese metal, and high purity manganese sulfide, these are really high value products if you can generate them from your manganese ore. And these are what are needed for lithium-ion battery technologies. A very quick look at some of the economics of these three battery metals. I'm not going to go into this in too much detail, but just a quick squeeze. We can see that nickel kind of fluctuates around this high teens into the $20,000 per ton. Cobalt's much higher. That's been flirting over the last few years between 80 and 120, but manganese kind of consistently below $10 a ton. If we stick that into a price versus a reserves table, as you would expect, we have this inverse correlation here where we have manganese with billions of tons of reserves globally, going down to cobalt, which is up around the $100,000 mark at times, with nickel up here. So that's what we'd expect. But if we think about the price of the high-value manganese battery products, currently manganese metal or electrolytic manganese metal is about $3,700 a ton, which brings it over here. So if we can find a way of cheaply converting manganese ore into high-value manganese battery products, then there's a potential to have a really significant industry focusing on manganese. And Australia is particularly well endowed with manganese, as is WA with manganese and all the other battery metals. But if we think about the bottlenecks that are expected to occur in the next few years, particularly for cobalt, which is the predominant source of cobalt is the Democratic Republic of Congo. In the next few years, that's largely going to excuse me, disappear from the supply chain for environmentally aware producers. So we can expect cobalt to really drop off way down here somewhere, and we'll have to focus on things like manganese to really step into the role of playing a dominant source of the battery metal resources that we really need to move into the coming phase of green energy technologies. So get all that out of the way. Let's discuss the geology of manganese and why we're here today. So the largest and most economically important types of manganese or deposits of manganese are sedimentary manganese deposits by far. And these are derived from ancient marine sedimentary deposits. So I'm not talking about the types of manganese deposits that are forming today throughout the modern era on slopes in the modern oceans, sometimes proximal to hydrothermal vents. I'm talking about ancient processes that have occurred throughout geological history. We can form manganese deposits in other ways, for example, via hydrothermal alteration of carbonates, but these are less significant in terms of their tonnage and how big they tend to get. And also we have manganese associated with banded iron formations, but I'm not going to talk about these today, but feel free to bug me about them at any point. If we have a quick introduction around the geochemistry of manganese, this is a bit of a dry slide, so I'll skip through it quite quickly. Manganese behaves quite similarly to iron, but depending on how knowledgeable the person you're speaking to is, kind of not really. It's a little bit more redox sensitive than iron, and a little bit more complicated. It has three oxidation states. Mn2 plus is the reduced, and Mn4 plus is the oxidized, and reduced manganese 2 plus is soluble in an anoxic ocean in the deep geological time in the oceans. And if you oxidize excuse me, if you oxidize manganese 2 plus to manganese 4 plus, it becomes insoluble and will precipitate as a chemical sediment. To add to that, manganese is non-chalcophile, so it's quite different compared to to iron in the geological record. In summary, it's a highly redox sensitive element, which is critical to how it's formed, and I'll go through that in just a second, if this works. Okay, to really set the scene, I need to give you a quick catch-up on the history of the atmospheric oxygenation on Earth. Apologies if I'm teaching you to suck eggs here, but it's important to lay this out before we talk about how and when manganese deposits form. So pre 2.45 billion years ago, the atmosphere and oceans were largely anoxic, if not entirely anoxic. There's a lot of evidence for some pre-Great Oxidation event whiffs, but that's kind of contentious. The post-GOE period may have potentially seen as much oxygen in the atmosphere as there is in the current period, but that's debatable. But what's assumed is that after the GOE, about 2.1 billion years ago, there was this period of probably quite low atmospheric and ocean oxygen, which was coupled with the emergence of a stratified ocean system, whereby we had potentially a thin oxidized layer at the surface, euxinic conditions around the shelf and slope environments with ferruginous anoxic conditions in the deep oceans. And of course we had the deposition of banded iron formations throughout much of the Archean, where there was predominantly anoxic oceans. I'll skip that, I don't need to see that. Too much information in one slide. Some of the evidence for an anoxic atmosphere pre-GOE includes things like detrital, sulfide minerals at surface and the lack of red beds. This is a drill core from the Tumbiana Formation in the Fortescue group, which was drilled a couple of years ago with cross-bedded detrital pyrite within a fluvial lacustrine succession. So this is quite strong evidence for a reducing environment in the around about 2.7 billion years ago. So there was a lack of oxygen to oxidize and break down these pyrite clasts. But then, of course, we lose banded iron formations around the 2.1, 2.2 period, certainly from 1.8, and that may be because of a reduction in availability of iron, or it might be through the development of euxinic conditions throughout the oceans, so the emergence of lots of sulfur in the oceans, which may sequester iron instead. That may or may not have happened. But what certainly is the case is we see evidence for oxidizing conditions in the terrestrial environment. So the emergence of sedimentary red beds in the surface environment, such as these here. So this is from the Lower Tuala group in MacArthur Basin in the NT, and this is a picture that Pete Haynes gave to me a couple of years ago about reduced spheroids within an oxidized red bed from the Elgin siltstone in the Kimberley Basin. And the oldest known red beds that we know of are about 2.15 billion years old in Gabon. But the biggest and single most bullseye evidence we have for the emergence of oxygen in the oceans is the emergence of gigantic sedimentary manganese deposits. So this is the temporal distribution as we know, or as the global literature knows, of how much sedimentary manganese there is throughout geological time. You can see that by far the biggest deposit is the Kalahari manganese field deposits in southern Africa, where there's well over a billion tons of manganese, which is present over a huge area. This is the biggest known deposit on Earth. But that quickly drops off, and by around 2 billion years ago, and certainly by 1.8, we go into this period of almost no manganese deposition at all, and this is known as the manganese hiatus, and it is coupled up with the idea that there was very little development or change in the global redox system, and there was no manganese deposition. There was very little happening and very little oxygen in the atmosphere. So if there's no oxygen in the atmosphere, you can't deposit, oxidatively deposit things like manganese. And this is deeply entrenched in the literature. It's very difficult to get the global atmospheric oxygenation researchers to see beyond this, but things are starting to change now. Sorry, this is also known as the boring billion outside of the manganese context. This 1.8 billion to 0.8 billion years ago period is known as the boring billion. Right. So how do these massive sedimentary manganese deposits form? First, you need the source of free oxygen, and apologies, this is a bit of a busy explanatory slide, but it has everything that we really need in this table here. First, we need the source of free oxygen in the form of photosynthetic oxygenation in the surface oceans, but we also need a source of reduced manganese 2+ in the oceans here. So that's typically hydrothermally derived from volcanic activity. And at the chemocline, we have oxidation of the manganese, and then it deposits as on the seabed. It deposits as insoluble manganese oxide. But then once it gets into the sediment, it's re-reduced to manganese 2+, probably microbially, but it's certainly re-reduced as into manganese 2+, and then in the sediment it reacts with carbonate, or it reacts with carbon to form carbonates, and there it's locked in the sediment usually as these microspheres of different manganese carbonate end members, and it's locked there throughout geological time. But then to form the big ore deposits, we need to tectonically uplift and exhume this and oxidize those manganese 2+ carbonates, and we oxidize those back again into manganese oxides. And that's pretty much it. And then in the supergene environment at surface, such as that we see in Western Australia, all of the other sedimentary rock-forming minerals, most of the quartzes and things are all lost over millions of years as well, and you end up with this very high-grade manganese oxide ore. Right. So the WA Manganese Belt and manganese potential here, which is what we're here to talk about. This map on the left, obviously, is a geological map of WA with some of the major manganese projects and deposits mapped out. We're not going to look at the ones in the Ilgarari. Those are mostly hydrothermal or banded iron formation associated, and I'll just say that the banded iron formation deposits are typically very low-grade manganese. What I wanted to focus on today is this belt through here, which I call the WA Manganese Belt. When we look at these in detail, we can see that they're really dominated by, or the host rocks are really dominated by the Proterozoic basins that surround the Pilbara and the Ilgarari cratons, and these are largely the Bryah Basin, which is about 2 to 1.9 billion years old, the Irahidi Basin, which is 1.8 to 1.6, Edmund Basin, which is an early Mesoprote basin from about 1.6 through to about 1.45, and the Collier and Oakover basins, which are late Mesoproterozoic, recently dated about 1.1 billion. But if we think about those ages in the context of the global sedimentary manganese deposition, that's all within this gap through here in this sedimentary manganese hiatus, where we've got this huge gap, and also occurs through this boring billion period where we have stratified oceans. So something doesn't really make sense there, and you look all the way through the literature, none of this is picked up in the sedimentary manganese literature in a global context. So it's been missed. They're well known, but it's certainly been missed. And if we look at the different deposit types, we can see things like supergene, residual, apologies if you can't see that if it's not clear, vein-hosted, iron-associated, nickel laterite-associated, carbonate-associated, stratiform. There's all these different terms. So if we focus in on this WA Manganese Belt, there's 717 entries in the GSW Mindex database in this area across all mines, deposits, prospects, and occurrences. But there's heaps and heaps of different deposit types. Not very few of them have the same explanation. But what they all share in common is that they're all supergene. They're all manganese oxide deposits that occur at surface. You could walk up to them and kick them. They're very easy to spot. So they've all originally come from manganese carbonates that have been oxidized one way or another. None of them were principally formed as manganese oxides, apart from the very, very minor manganese oxide laterites which are forming today. The big ones are all formed from the oxidation of manganese carbonates. But almost nothing had ever really been done in terms of research on how these deposits formed until recently. And in the last few years, we've been working on a few of these. So we've worked on the mango deposits through the Edmund group, the Butcherbird and associated deposits in the Collier group, and the huge number of satellite deposits around the Woodie deposit and in the far north of the Oakover Basin, which apparently doesn't exist officially in the GSWA, but still exists nominally. Maybe Peter can explain that a bit later on. So if we look at where those occur in terms of the stratigraphy, we have stratiform manganese mineralization in the Ilgarari formation in the upper Collier group, and the lateral equivalent, which is the CSIRO formation. This hosts the Woodie mineralization here. And we also have huge mineralization in the Ullawarra formation, which is in depositional package 4 in the Edmund group. This upper age limit's about 1.45. So we have huge manganese occurrences in the sediments that are about 1.1 and about 1.45 billion years ago. So that would be one here, and in here as well. This is a deposit in northern China, which is basically the outlier of the manganese deposits in the Mesoproterozoic. So in terms of what we understand from the literature, there shouldn't be huge manganese deposits in these rocks, but there are. So if we look at the biggest one, the Butcherbird formation, which is in the Ilgarari formation, this is late Mesoproterozoic here. This is what it looks like at surface. We've got this massive supergene cap of iridescent blue, certainly how my eyes see them, is iridescent blue manganese oxides at surface that form these huge, big, massive caps. And then these are below that massive cap, you have these interbedded weathered red clay siltstones with some minor supergene layers in between. And this is some of the textures of the rocks that come out of that, formed of these nodular manganese oxide lumps that come out of this stuff here in particular. This is all massive without much form. And these are some secondary lateritic paleochannel deposits that kind of subcrop further downslope. This is in here, just to give you a bit of context. So this is the largest manganese resource in Australia, currently 263 million tons, and is also the 5th largest global manganese project. So this is what the massive manganese oxide cap looks like, and this is what it looks like as a conceptual 3D diagram. We've got this supergene cap that's kind of collapsed on itself at the surface, lost all of the other siliciclastics, and we're left behind with just the manganese and iron oxides. And then below that, we've got these minor supergene layers where we have interbedded red, pink, cream-coloured clay minerals interbedded with these minor manganese oxide beds. And then below that, we've got unweathered siltstones of Mesoproterozoic age, where we have interbedded with pyrites and these pinkish manganese carbonates. This is a big bed of rhodochrosite through here. We've been lucky to get access in the last few years to one of the only drill cores that have ever gone into this manganiferous stratigraphy and tapped into the unweathered stuff, which has given us the window into what these rocks look like in their unweathered state. So we did a bunch of detailed work on this as part of the Capricorn Distal Footprints project back in 2014. And what we noticed was that even though below the supergene zone, where we have these interbedded supergene manganese oxide layers, we actually have these big thick beds of manganese carbonate. So we're looking through the weathering profile, and we're able to see what the primary manganese carbonates look like. We did some iron speciation on these rocks with Stanford University. Iron speciation is one of the most robust Paleoredox proxies that we're able to do. And what we really noticed was we have this fluctuation of iron reactive species ratios, which I won't go into details of it, but it basically shows that we have fluctuation of oxidization and returning to anoxic conditions. So we're going from anoxic to oxic conditions in this part of the slope through here, which also sees the deposition of these big thick beds of manganese carbonates. So this is quite good evidence for a cyclic nature of the deposition of manganese oxides, which are then converted to manganese carbonates, being driven by the oxygenation of Mesoproterozoic oceanic basin. If we compare the mineralogy of those carbonates with the gigantic Kalahari manganese field and some of the other massive Phanerozoic deposits, we can see that the mineralogies are the exact same. We're really looking at things like anchorite, kutnohorite, rhodochrosite, which are our primary manganese carbonates, and we see this in all of the major sedimentary manganese deposits across the planet. So it's really good evidence for this deposit being formed by sedimentary manganogenesis in the same way as the massive ones worldwide. But we can also see the evidence of that in the supergene zone. So those microspheres that we see through here in the carbonates, those are actually preserved in the supergene zone as manganese oxides. So if we look at these interbeds where everything's not completely, where all the sedimentary textures aren't completely stripped, we can see that these microspheres are actually preserved as spheres of goethite and potassic cryptomelaine. Whereas if we look at the supergene cap, it's formed of these massive cryptomelaine and iron oxide minerals. Quite often there's really complex paragenetic sequences of overlapping veins and veinlets of these different manganese oxide phases with the associated iron. There has been work attempted to date these, and the last weathering events that formed certainly some of the latest cross-cutting veins is as far back as the earliest part of the tertiary. So it looks like there's been constant supergene upgrading since the tertiary, but some other tentative dating suggests that there might be weathering as far back as the Permian glaciation, and then some of the later wet, humid tropical periods after that. So it might be that these have been constantly upgraded all the way through from the Phanerozoic, certainly from the Mesozoic onwards. And we've been doing some quantitative mineralogy on these as well in the ore zone where we've been able to pick out different end members of the manganese oxides, which is important from an ore processing point of view. If we look at the slightly older deposits, the manganese deposits, which form this belt through here. So this is actually an 85-kilometre long belt of continuous exposure of manganese oxide cap. This is what it looks like if you look along strike. This is actually quite a high hill just north of Mount Augustus. And that is a continuous ridge of a thick manganese oxide cap that runs, as I say, for at least 85 kilometres through here. This is what it looks like in the interbeds. Again, we've got this interbedded black, blue manganese oxides interbedded with the more ferruginous clays. And this is in the Ullawarra formation just here in the about 1.45 billion year old package, upper package of depositional package 4 in the Edmund group. So from that outcrop here, from deposit Mango 4, this is the conceptual cross-section that we have. So we have these pods of minor mineralization through here. We have a massive supergene cap which has been exposed, but it actually has a couple of units sitting on top of it with the dip of the rocks, and we have this old preserved paleo channel which is preserved as mesas through here of ferruginized and manganese enriched Pisolithic material, which is actually quite high grade. Its grade is almost as high as the massive supergene cap, which is above 30%. So we have really high grade material sitting on top of this ridge for about 85 kilometers. So sure, this material here isn't primary in terms of it being primarily sedimentary manganese, but this stuff certainly seems like it might be, because it shares a lot of similarities with the stuff that we see in the Collier Basin. And yeah, we also have these minor manganiferous pods down through here as well. Unfortunately, we don't have any drill core that goes through this material, so we're not able to do the same detailed studies in terms of the geochemistry and formation mechanisms on this material, because we don't have access to it. But if we did put a drill hole through here, for example, we would be able to get into that and have a look at it. And again, we've done some detailed work on what the ore mineralogy is, what its trace element geochemistry is, and we can see that we have these very complex relationships of potassic cryptomelaine that's forming within quartzitic ore. And there's also quite high iron content in this material as well. That's actually the same image that I showed from the other one. I've mixed things up a bit, but you get the point. They're quite similar. So if we look at the major deposit that's producing in the area, the Woodie deposit, which is the one that many people might know of. So this is up here in the far north of the Oakover Basin in the eastern Pilbara, just on the western margins of the Patterson origin. So this is actually, these rocks up here, which are part of the Oakover Basin, are the lateral equivalents of the stuff from Butcherbird. But for a long, long time, it's assumed that the mineralization at Woodie is Archean in age, because a lot of the high-grade stuff sits within these fault zones within the Currawine Dolomite. As very little work had been done on this until Sarah Jones started working on it a few years back. But the easy thing to assume would be that this fault zone is hydrothermal manganese, which has then put all of this manganese material in the overlying rocks into it. Whereas what we think now is it's actually the other way around. We had this huge body of anoxic manganese 2+ bearing water that sat on top of this on conformity, and the presence of manganese or anoxic manganese bearing marine water was able to alter the carbonates in here to manganese carbonates, and then when it's all been and then we've got, of course, the sedimentary manganese process which occurred throughout the manganese group Oakover Basin sediments up here, all of which has been supergene enriched. So we now think it's not primarily Archean hydrothermally derived, it's the other way around. It's top down. So if we look at the cumulative resources that we have for Woodie and the surrounding related satellite deposits within the Oakover Basin, those have a resource of about 255 million tonnes, but there's heaps and heaps more that haven't got any resources attached to them. So if we think about those three examples in the context of sedimentary manganese occurring at 1.1 and 1.5, if there was a manganese hiatus, so if sedimentary manganese deposits weren't able to form back then, why do we have so much? Why do we have hundreds of millions of tons, at least, of manganese in these rocks? If we look at some of the more recent research that's been coming out in the last decade or so, there's actually a lot of evidence for at least temporary atmospheric and ocean oxygenation events, at least locally and at least transiently, at about 1.1 and 1.4 billion years ago. Here's a few diagrams that I've stripped from a few papers that have suggested just that. This is one which focused on sulfur isotopes that I worked on during my PhD, where we highlighted 1.0 and 1.2 billion year old lacustrine shales that had big sulfur isotope excursions which were consistent with oxygenation of sulfate. Here's one we did in 2015 where we had huge molybdenum enrichments in lacustrine shales about 1.2 billion years old, so somewhere between 1.1 and 1.2. Here's one similarly which shows something around 1.4, which again is moly TOC, so the same as the stuff that presented a second ago. And we have similar things through here. We have enrichments about 1.1 in, glasses aren't working anymore, calcium magnesium ratios, and again through here with rhenium and black shales. So there's a growing body of evidence, at least spurious evidence, globally in black shale environments that we do have something going on at about 1.1 and 1.4 billion years ago. So where does all that fit in with the so-called manganese hiatus? If we think about the fact that what I've just shown you, we have resource estimates from only 2 groups of deposits among those 313 prospects and projects really, not including the 717 entries there are. In the Collier group alone and the manganese group, that gets up here into the high 500s, but there's heaps and heaps of other occurrences in the rocks of the same age which don't have any resources attributed to them. So we're probably up here somewhere in reality in rocks of that age. In the Edmund group, which includes that big long 85 kilometre long occurrence of thick manganese oxide accumulation, we don't have a resource estimate for that, but a quick back of the envelope calculation, which of course isn't very robust, brings us up here somewhere, but that's only that one occurrence. There's quite a lot more in that unit. But then of course we've got the Bryah Basin and the Irahidi Basin as well. We don't have any accurate numbers for those, so it starts to become a very, very unwieldy challenge to start to count how much manganese there must be in this manganese belt, given that we don't have very many, well basically none, when it comes to resource estimates. What we can do though is we can just plot these into time space and say in the Bryah Basin we have a whole heap of sorry, I'll go back a second. The Earhedy and the Bryah Basin, they do make sense in being sedimentary manganese deposits. That's not too controversial, because they're just on the back end of this Paleoproterozoic manganese depositional period. But these two aren't. But if we start to fill in this global picture of temporal manganese deposition, you can see that WA alone can fill in this manganese hiatus quite nicely, and it's quite clear that WA hosts an awful lot more sedimentary manganese than has previously been recognised. So in terms of key outcomes of what we've learned over the last few years alone, we still basically don't know anything, right? Is the deposition of gigantic sedimentary manganese deposits within the manganese belt were formed from the sedimentary manganese ore forming processes, which formed the huge ones, the big economically important ones elsewhere on the planet. Although, yeah, we do need to do more work on the Paleoproterozoic stuff. I purposefully haven't included the Earhedy Basin stuff in here because I've never actually got my foot on them yet. I'll get there eventually. I purposefully missed the Earhedy Basin from the Manganese Belt in the first couple of slides, and I've misspelt it there as well. I need to fix that. But the point being, we have a huge amount of sedimentary manganese in this belt through here, not including anything that's in the banded iron formations, and not including any of the other minor deposits which occur through different processes. So I haven't touched on today the manganese oxide deposits around Abra, for example, which we've also looked at, and those are formed from the hydrothermal alteration of carbonates along the structure which hosts Abra. There's quite a lot of that in this area. We haven't looked at those, but those aren't the ones that are going to form huge, big deposits, particularly undercover. What we're looking at is this big belt through here, plus this, plus or minus these. So in just these alone, we have a huge amount of manganese, and we don't even know how much there is. So in terms of conclusions to take away, in terms of a future battery industry, which Australia has aspirations to have on shore, manganese will play an important part of that, purely through the cost economics of nickel and cobalt, and the current use trend of manganese in things like electronic vehicles and power tools. Manganese will have an important part to play there, but we're already well endowed with the existing high-value battery metal resources. But we can now recognise that we've got globally significant manganese resources as well. However, we've only just scratched the surface in terms of understanding some of the aspects of these ore deposits. We know almost nothing spatially about the mineralogy, what the ore mineralogy is, how it could be processed. So this is something that we need to look at. But what we can definitely say is that WA is well placed to be a battery metal hub for a future battery industry in Australia. And in the current era that we live in, that can only be a good thing. Thanks.